Ladies and gentlemen, welcome again on our presentation. This Thursday we would like to tell a few words and introduce those of you who are not so familiar with techniques called high-resolution carbon-14 NMR, especially dedicated for solid-state investigations. Before we start, I would like to tell you that this presentation was prepared by my friend Monika Makrocka-Ryzyt, who couldn't take part in this conference, but luckily we believe that she will be next time and will tell you much more because she is an expert in this field. Jacek, you know him, is on the NanoBioMedical Centre and now is looking for you, so you have broadcast live connections via the internet. And after my theoretical explanation, which goes through parts like a nuclear spin interaction in the solid state, high resolution solid state techniques, we tell about few methods to remove dipolar decoupling, then magic angle spinning, or saying another spinning at a specific angle, and then cross-polarization. Jacek shows you some examples of these techniques, okay? So, as a first, I would like to tell you the difference in a very simple way about the liquid state and solid states. So, as a physicist, chemist, biologist, maybe medicine people, you know that liquid systems from their nature are completely different than solid systems. First of all, in NMR techniques, also EPR techniques, the line width for the liquid state are rather narrow, 20, 10, sometimes more narrower than for solid state system. In condensed matters, usually at all, interactions are so broad, the couplings are so broad that the registered line shapes are also very broad. Very often, for example, in dipolar interactions where they have line width comparable to tenth or hundreds of kilohertz. Sometimes in the quadrupolar systems, the quadruple coupling constant is close to 1 or 2 or 3 or 5 megahertz. So it depends on what you wish to study. This slide represents something which is very well known. Most of you are familiar with this equation. Nevertheless, I would like to draw your attention at the two first part of the main Hamiltonian. This is a Zeeman and something which is very important in our discussion because RF field interaction represents this interaction which is responsible for interaction with the external magnetic field. External magnetic field, this is the field which is outside the investigated systems. Mostly of us know what is external field. This is B0 field, but irradiation produced by the external RF field is also external field. The rest of the Hamiltonian in this equation represent internal interactions which are inside the investigated system. So, as you can see, dipolar coupling is a coupling between spins possessing spin a half. Sometimes homo or heteronuclears. Okay, this is well known. Quadrupolar interaction. This is interaction between sometimes dipolar spin and quadrupolar spin. Sometimes only the quadrupolar nucleus itself. And the last one, chemical shielding, which is the feature which have place because of the electrons flowing surrounding nucleus which we study. Trying to understand the idea of the condensed matter physics system for solid state, we have to recall the idea of dipole-dipole coupling. At the left top of this slide, you can see the main equation which consists with two very important parts. The first one is scalar coupling with the spin I and S represent in the direction Z, because in NMR usually we should understand the population, the interaction in the Z direction, and something which is called the structural factor. A structural factor is an element which defines the orientation of the main axis of interaction to the external magnetic field, which is responsible for creating the distribution of populations. And these interactions change the energy levels, especially if the direction is changing. This theta angle is called usually as a horizontal angle, and sometimes in quadrupolar system, angle phi is called azimuthal angle. Nevertheless, changing the orientation of the intervector to the direction of external magnetic induction field is main source of changing the energy levels of the Zeeman interactions. And in a case of distribution of these angles, we have three situations now presented in this slide. The first one is in the situation when all these directions are the same and they are oriented to the external magnetic field in the same direction, so they are parallel. And the distribution of frequencies in such situation is like that we have two lines corresponding to the central frequency. And if we hide this orientation of this nuclear vector to the perpendicular direction, the position of this light also change. And the distribution, of course, of these frequencies change also. And finally, if the orientation are randomly distributed, so they create isotropic situation, we take the very scarce pattern called Peg doublet. This is at the bottom, okay? And again, these lines, as you see, create the distribution of the frequencies, resonance frequencies, which are much broader than for the liquid state. The next issue which we should, in our discussion, is a chemical shielding. Chemical shielding is a phenomenon which is very useful for chemists, especially if you are interested to study structure, as I said before. And it comes from the electron moving around the nucleus on the special trajectories called yes, I mean about SP, SP2, delta, P pi. Yeah, orbits. Exactly. Thank you. So, they create their own magnetic fields because each charge which is moved generate magnetic field. In this case, these magnetic fields are directed in the opposite to the magnetic field, which make the orientation of the magnetic moment. So finally, because of these orbits, which sometimes possess very crazy shapes, these currents generate different additional values of local fields, changing the frequencies of the line width for each independent nucleus. And we use this in the high resolution spectra very often. So for solid state, the situation is a little bit tricky because molecules have no freedom to move slowly. There are constraints in the geometry of the neighbors which not allow them to tumbling freely, to in fact average the local fields. So therefore, some molecules, some systems, even if they have the order of freedom, for example, in the methyl group and the CH2 groups located or joined to the main axis, like in polymers, sometimes in like in crankshaft motion in polymers, they make something which can be used, can be described like an averaging, but this is not at all. This averaging is only in one direction or two directions sometimes. So this is not isotropic averaging. And therefore, the orientation of molecules to the external magnetic field define the orientation, and therefore, as you showed before, from the relation of the dipolar Hamiltonian, in the nominator 1 minus 3 times square theta defines the value of energy splitting between these positions. So, for example, on the left side, of the right side of this slide, you have three situations of the molecules, ring, positioning at three different possibilities to the external axis, the main axis of the external field, like that the distribution of the parameter sigma 1 1, and that is like that, giving the spectra at this position. Then in another position gave the spectra in this frequency, and finally, as a superposition, you have a shape like spectra for isotropic distribution. And this is easy to imagine that as a scientist, we use tables collected together in the whole world, allowing us to find the position of each line, especially if we don't know what we cooked in pot. This is very used method to study the structure which we try to achieve. And now I would like to go to the main topic of this presentation. As you see, we have many problems to overcome in solid state investigation. So one advantage of the use high resolution carbon-14 techniques in the solid state is that they have a range of the chemical shifts, and they are easy to distributed to shows for different nucleus creating substance. And most of the systems are system possessing organic properties, like for example food, like for example animals and so on, and therefore they are very interested to be studied. So this advantage is one very important, that carbon-14 is rather rare elements in the world, because the natural abundance is only 1%. That means that 99% of other carbons are not magnetically active, and the signal to noise which we can collect is very low. So the second is that zero magnetic ratio, that is the value which exists in the omega 0 gamma B0 equation, defines the frequency of moving, rotating angular momentum around the axis of external magnetic field. And from the technical point of view, if you have lower frequencies, the system which is used to study such nucleus generate higher noise, and the signal is also lower. So therefore, signal to noise ratio is also lower. And the third one, but not the last, I think, the most important is the relaxation times. That means that the system is relaxing after irradiating very long. So sometimes it is good, sometimes it's not so good. For example, these relaxation times are of order 10 or 100, sometimes 1,000 seconds. But this is luckily much more likely than, for example, for silicon. Silicon is a nuclei which has rather long relaxation times. So Now I would like to introduce three ideas which allow us to study solid systems. The first one is dipolar decoupling. This idea suppresses direct dipole interactions between two adjacent or by bond or sometimes by space nucleus. Second is magic angle spinning, or I think rather it will be say the spinning at a specific angle, and we will discuss a little bit later about this, and cross-polarization idea. So, what is dipole-dipole interaction? We know dipole-dipole interaction describe the situation when two spins interact through the space or through the bonds together, and one influences the second one, so the frequencies change for both of them. Therefore, both of them have different frequencies, larval frequencies, and can be observed in the NMR spectroscopy at different positions. So therefore, somehow we can remove these interactions. And there are many methods which can remove these interactions, generating or locking one of the spin in the specific direction. So interaction spin-spin can change, can transfer the changes in the interaction in the Hamiltonian, and therefore the best way is to lock one of these processing moments apart from the second one. And now there are a few acronyms. For example, the first one is continuous wave. You can put the fast irradiation for one steady long frequency at the power matched to the coupling constant, and the problem or issue for this method is if they have fast elements, that means fast structures elements, you can overheat the system. So this is not a good idea, especially if you have a water system or flexible parts of substance. The better idea is to use two-pulse phase modulation, which uses two pulses with rather small angle and different phase. But other methods, like for example walls, MEF, GARP, etc., also are very popular use, especially for the very complicated polymeric system or biologist samples. And second idea, apart from the removing dipolar coupling, is to simplify physical state, state of substance to be a liquid-like. Of course, this is not possible to change a solid to the liquid. From physics, from the primary school, we know that it can be also possible to heating the system, but we would like to stay this system the same. So we can make something like averaging of the interactions, that averaging local fields, turning the system very fast in the frequencies comparable to the coupling of interactions, to the splitting of them. And therefore, if we rotate the sample inside, which is our substance, at the specific angle, you remember the equation at the beginning with the 3 times cosine squared theta, which after the equalizing it to 0 can give us the theta value 54.55 seconds. The dipolar and chemical shift anisotropy will be averaged. So this is the reason to use the spinning at the specific angle. So not the magic angle spinning, but spinning at the specific angle. And we call this angle magic. The first idea is to make somehow the population state of the carbon much more rich. We said at the beginning that we have only 1%. If we imagine your molecules which you are interested in, For example, benzene, for example, you see that there is 6 carbons, so probable none of them is magnetically active, yeah? Because every 100th is magnetically active. So sometimes if you study small molecules and the number of carbon inside in them is not 100, it can be possible that in one molecule, no carbon will be magnetically active. Of course, there is a method to reach the system by the isotopic chemical methods, but usually this is very, very expensive and sometimes not possible. So if you see the screen on the left side, you have the graphical representation of the distance between 2 levels, because we have still the proton, that means the nucleus of hydrogen 1, at the selected magnetic field. On the right side here, we have the same situation, but we know that the gyromagnetic ratio defines the distance between energy level around 4 times lower. Okay, so how we can change the population here, or how we can change the population here? We can reach the population here only if these 2 systems will be equalized to in the same energy levels. It is possible to make this by using the fast alternating B1 field in this system and the same in this system. So we put into the B1 coils, which is constructed like that, with single coil. It consists with 2 resonance circuits, 2 frequencies with the matched power and the Z direction of the X direction of the field B1 represents and change the distance between 2 levels on the proton, and because proton is much more populated, it's very rich, it transfers itself the populations state, reaching the population in the carbon reservoir. So this method is very often used also in the Aber's rare nuclei and allows us to get the higher signal in the carbon-13 spectroscopy. Now I would like to show you some elements. This is a rotor. Inside we put the sample. Of course, this is for those of you who never make solid-state experiments. The diameter of the length of the rotor is designed for the length and the diameter of B1 coils, which is detected coil. Some equipment which are used to prepare the sample, because sometimes you can use measurements on different systems. I mean about different nucleus. You have to use also different type of spinners. For example, not having the protons. So on the left is zircon oxide, macro, this is a kind of polymer, boron nitride, and caliph and vespol. And probe head, which is located in our lab at the bottom of the magnet, is loaded by hands. This is probably my hand, I don't remember. Okay, so I know that this very fast introducing to solid state is not to be enough to understand, but I hope that after that we'll have to discuss, and if not, I am open to discussion. Okay. Jacek, thank you.
Okay, can you hear me? I hope you can. So, hi again, guys. I have already introduced that system on Monday, so you already know that. This is our 9.4 Tesla system designed for solid-state experiment. So this 400 megahertz spectrometer is equipped with the solid-state probe head. And maybe before we start experiments, those basic experiments, I would like to briefly describe you the probe head itself. So I would like to show you several features of that probe head, because we have two different probe heads which are very, very similar. One of them does have rotors which have 4 millimeters in diameter, and the other one has a slightly larger rotors, 6 millimeters in diameter. And the latter one I have over here. I'd like to show you several interesting features about that probe head. So let me maybe magnify the screen here. Yeah. So that's the probe head. So Zbigniew has already presented several pictures, but I would like to show you how the stator looks like. And I would like to also show you that its position is not coincidental, let's say. So as you can see, I hope you can, the stator is over there, and it is tilted slightly with respect to the main axis of our, let's say, this body axis of our probe head. And this is done on purpose because this stator is inclined at a certain particular angle, which is called magic angle. And in fact, this is 1/2 of so-called tetrahedral angle. And at this so-called magic angle, we can then perform experiments, and we can average out, at least partially average out, certain interactions, for example, dipolar or chemical shift anisotropy. And within that stator, you can place your rotor, and you can develop so-called air cushion. So you make your rotor levitating, and once the rotor is levitating, so you simply reduce the friction between the rotor and the stator, then you can apply an additional pressure to the propeller, because every single rotor does have the propeller at one end and one side. And applying this extra so-called drive pressure, you can accelerate the rotor, and because there is no friction, it can rotate quite fast within the stator, under magic angle conditions, of course. So we can reach, for certain probe heads, we can reach dozens of kilohertz frequencies. For this particular probe head, we can reach only about 10 kilohertz, because our rotors are relatively large. For the one which I'm going to use today, which is installed just underneath my magnet now, we can reach 18 kilohertz, which is relatively fast. However, for biological samples, we would like to have much faster rotation. And okay, because why it's necessary? It's necessary because we would like to somehow mimic, Zbigniew mentioned that, we would like to mimic liquids, right? So we'd like to introduce certain motions. And additionally, we introduce certain trick, because when you look at the orientational component of the dipolar Hamiltonian, then you can instantly notice that there is this second polynomial, Legendre polynomial, which contains this theta angle, and this is this so-called magic angle, right? So let me maybe first introduce very simple experiment, and we would like to really measure the same sample which we had measured on Monday. That was our hexamethylbenzene, very simple molecule, very simple system. and this time, which is of course solid state material at room temperature. At room temperature, this is semi-crystalline material. We have a powder sample, so which means we have a number of different tiny crystals within the rotor, and their orientation with respect to the external magnetic field is completely random, let's say. Of course, you can also work with monocrystalline samples, but you have to have slightly different probe heads. Usually, in a solid state NMR, you work with powder samples, so you have polycrystalline samples with randomly distributed tiny crystallites within our rotor, which means that you expect having a distribution of chemical shifts due to distribution of orientation of your chemical, for example, of your chemical shield tensor, for example. All right, so very simple experiment. This one is probably, I would like to magnify now the display. So this is our carbon-13 channel. We would like to irradiate it simply by 90-degree radio frequency pulse. Simply, we would like to excite the system, and then we would like to listen what the system is going to tell us. So we would like to acquire FID, and then after Fourier transformation, we will observe a certain spectrum. And what I would like to maybe add here is that this is the simplest possible experiment you can imagine, really, because you simply apply one radio frequency pulse, that's all. So let me maybe start the experiment now. And moreover, this is so-called static experiment, which means that our rotor is placed within the stator. However, it's static, so there is no spinning introduced yet. So we have static experiment without dipolar decoupling. And the second experiment I would like to show you in a minute is gonna be exactly the same one, but with dipolar decoupling introduced during detection period. So at the moment we do not have dipolar decoupling, which means that we have strongly coupled carbon-13 and protons with protons. So, which is in that particular case may produce relatively broad spectrum. And as you can see, this spectrum is not clear. Its quality is, let's say, not satisfactory at all. However, let me just show you once more the structure of that molecule. We can instantly see that there are two, at least in this case, there are only two inequivalent positions of carbons. One residing in this methyl group over here, yeah, and the second one that's carbon residing in the phenyl ring. Okay, so as you can see, we can, even for the static sample, solid state sample, we can somehow recognize that there are probably two signals over here. However, the quality of the spectrum isn't satisfactory at all. So we would like to somehow improve it to make it better, to at least make it more high resolution, let's say. Okay, so let me introduce the first trick now. We would like to introduce dipolar decoupling. So we'd like, so in that way, so now the pulse sequence looks slightly different. So we have excitation pulse on carbon-13, but just right after this excitation pulse, we apply a train of pi pulses with different phases on the proton channel, and that gives us an extra, let's say, heteronuclear decoupling, because we somehow saturate the proton reservoir, and in that way we reduce quite substantially the heteronuclear dipolar coupling between the protons and carbons. So we expect that this trick should at least should improve our spectra because we reduce dipolar coupling between the carbons from methyl groups with adjacent protons, right? So let me try if that works. So I can, so that's exactly the same experiment, the same transients, the same acquisition parameters, except the fact that we have introduced this extra dipolar decoupling during detection period, during acquisition simply. So, yeah. So on the right-hand side now you can see the static spectrum without dipolar decoupling. And in a second, on the left-hand side, we are going to see exactly the same spectrum, but with dipolar decoupling introduced. And just a few seconds and we're gonna have it. All right, so as you can see, the spectrum is, at least the signal on the right-hand side over here is much better, it's much narrower, and its amplitude is higher, so it somehow resembles signals which we can distinguish on the solution-like spectra. So let me magnify maybe here that area. So that particular signal belongs to the carbons residing on the phenyl, not on the phenyl groups, but on the methyl groups. So you see that introducing heteronuclear dipolar decoupling, we reduced that coupling and we made this signal more pronounced over here because it's much narrower now. Of course, this dipolar decoupling haven't affected much the carbon signal coming from attributed to phenyl ring, which is obvious because there are no adjacent protons nearby, right? So, but at least this particular signal coming from phenyl groups looks much better, and it somehow resembles the liquid-like spectrum. So let me now introduce magic angle spinning. So we would like to spin our sample and without changing acquisition parameters. In order to do so, I would like to go to, maybe over there. I will just show you. Over there, just behind me, there's this magic angle spinning controller. But before I reach the place, I have to take off my headphones. Okay, I hope you still hear me. So I would like to manually accelerate the rotor, which is inside of our proppet, which inside of our stator. So in order to do so, I have to first increase so-called bearing pressure. So this bearing pressure develops so-called air cushion within the stator, which means that introducing it, we make our rotor levitating. So when the rotor levitates, the friction is substantially reduced, right? The friction between the rotor and the stator. So it's neglected, let's say. And then I would like to introduce drive pressure using those knobs here. And this, I would like to gently increase this drive pressure, aiming directly at our propeller now. And over here at this display, you can see how the frequency of rotor rotation increases gradually with an increase of drive pressure. So we have already 2000 rotation per second, and I would like to reach 5 kilohertz. Sometimes it is worth imaging that the beauty of that device, really, because you have macroscopic object spinning with enormous frequency. So it is very important to pack our material very carefully inside of your container made of zirconia, because you have to make sure that the center of mass of your sample is placed on the main axis of that rotor. Otherwise, you have momentum, the inertia works against you, and you may simply destroy not only the rotor, but also the probe head itself. So we have almost there. I reached 5,000. I will switch now to the automatic mode. And this box, it's clever enough to stabilize our rotation. So when the MAS controller is satisfied, then we are going to see this green light here. And that gives us a message that, okay, rotation is stable, rotation is locked, which means that there are fluctuations of the order plus minus 2 Hertz. And probably in a second we are going to see this. So now the system is fine. Our sample rotates steadily, and we can try acquire the spectrum now under exactly the same conditions, and we shall see if there is any change or not. Okay. Oh. Over there on the right hand side, maybe I will recall the spectrum recorded just a minute ago. And on the left hand side, in a few seconds, we are going to see our spectrum with magic angle spinning. Okay. All right, and that's the difference. So once again, maybe on the right-hand side, I will show you the one with dipolar decoupling, and on the left-hand side, you can see the difference clearly. So that's the spectrum with magic angle spinning, and that's the same spectrum, under the static conditions, right? So Zbyszek, can you still hear me? Because my colleagues, they have some issues.
Yeah. You may continue. So there are questions. Perhaps there are some questions.
Yeah. It's fine because we have issues from the other class that they lost connection.
Okay. There's a problem with the connection with Igor, but it's
okay. But over there, it's everything is fine.
Okay, yes.
Okay. So okay. So far, do you have any questions? But maybe let me just describe. I would like to say a few words about this spectrum because, as you can see, there's a dramatic change over here. Instead of 2 lines, which we have expected, we surprisingly observe much more lines over here. So there are more signals. Surprisingly, they appeared somehow, and you can, looking for the first time at this spectrum, you can, for example, claim that, okay, each individual line comes from the different inequivalent position of carbon, which is not true. So you have to be really careful interpreting and analyzing this solid-state spectra, because the only so-called isotropic line, which is real, let's say, is this one. So this one represents the line which we would expect having on a, let's say, solution NMR. Might be very close to that position. When we would, for example, had a solution of that molecule, then we would observe very sharp line somewhere in that range of frequencies. But those lines would disappear then. In solid-state spectra, we have so-called rotational sidebands present on your spectrum. And they are here due to rotations, due to time-dependent interactions, due to rotations simply introduced by our MAS technique. And it's very easy to distinguish the isotropic line from the MAS sidebands, because the distance between the isotropic signal and the satellite line, which rotational sideband, is equal exactly the frequency of rotation. So the distance over here is now 5 kilohertz, because our sample spins with a frequency 5 kilohertz. And as you can see, the distance of between the first order rotation sideband and the second order rotation and sideband is exactly equals 5 kilohertz as well. And on the left hand side, it's the same story. And the other thing is that we have some sort of asymmetry over here. So as you can see, this rotational sidebands pattern is asymmetric. So this asymmetry represents the tensorial nature of our chemical shield interaction. So you can even analyzing the pattern of your rotational sidebands, you can tell something about the shape of your chemical shift tensor as well. Just imagine increasing our rotational magic angle rotation. So for example, we can increase spinning speed up to, for example, 6 kilohertz. So then we would expect that signal would remain stable, would be exactly at the same position, that one over here, which is isotropic. And we would expect the rotational sidebands coming farther away from, going farther away from the isotropic signal. So we would expect one signal being here, whereas on the other side, the signal, this rotational sideband would go farther away towards the left-hand side. And, well, so this spectrum gives you a hint that you can really perform solid-state experiment, and you can, at least for carbon-13, you can reach high-resolution spectrum, which nicely defined positions of your resonant NMR peaks. Of course, for more complex systems, you can expect much more signals, and probably they are going to be more difficult to analyze. However, there are several techniques which allow you, for example, get rid of rotational sidebands as well. But for the sake of that particular presentation, we don't have a time, and probably I want to show you today those techniques. I don't know, Zbigniew, if we still have a time to continue and to show cross-polarization experiment, or? Yes, do you have a questions?
Yes. Yeah, so where does the other peak not have sideburns?
Well, could you once more, because we have, it's quite tricky to
I think it's this.
Yes.
Yeah, the disc serves as a microphone, I guess, so you can use it.
So why does the other peak not have sidebands?
All right, that's a great question, actually, because, well, it doesn't. As you can see, first of all, the methyl groups is very mobile. So from the point of view of dynamics, it's like say electronic environment is already has a very isotropic nature, which means that we do not have a chemical shift anisotropy in that particular case, in case of methyl groups. So you can imagine that the carbon 13, which resides on methyl groups, it's very isotropic in terms of electronic environment, which means that you won't observe rotational sidebands for that particular position of your nucleus. However, whereas your phenyl ring, on the contrary, has completely different nature. So its position with respect to external magnetic field is crucial, because you can imagine that there is, for example, this ring current present over there. So the chemical shift tensor has completely different shape than the spherical one. For example, it's fully anisotropic. So its position with respect to the external magnetic field decide about the chemical shift, really. Is it right? Is it fine, guys?
Yeah. Can I ask for? So, if you want to integrate the signal, do you have to account for all of the peaks and the sidebands included?
Okay. In that case, well, to be honest, that's a good question. I would, if you would like to integrate now, yeah, I would say that you would probably have to integrate over the sidebands as well, but I'm not sure about that. I don't want to mislead you now. What I would do, I would increase the the speed of our rotation of our rotor, and then at some speed you would simply for example, rotational sidebands would vanish, and then you could integrate your central isotropic peak, and then you could somehow assess the population, I would say. Yeah.
May I add something to your question? In the carbon-14 measurements, there is a small problem which is not easy to overcome, because different nucleus at different position possess different relaxation times. So, for example, if you irradiate very well and in a very well-defined p half poles, for example, for carbon-13 in the methyl group, the same is not for the ring. And this is one, so the population is not populated as well in the same way. So this is, second is a relaxation. So if you not understand that we should wait for a long time for the relaxation time, five times T1, for the observation of T1 of the methyl group, the same is not the same for the other types of carbons, and therefore the spectrum is not the simple summation of the number of angular momentum processing in the space. So this is not like in the high resolution spectrum, because in the high resolution spectra the relaxation times also sometimes are different. but usually they are very short in comparison to the solid-state system. The third one is that dipolar interactions also change the relation, the relaxation, and the process of equalizing states. So, for example, this problem appears very often in the biologists' investigations. For example, for protein or small substances, that means that the time and the dipolar interaction is not well decoupled. So therefore, there are different methods of decoupling. One are better, the second are worse. So this is the reason why we can't simplify that the area integration below the line exactly represent the number of processing momentum in the substance. Yeah?
Exactly, it's not as easy as in the case of solution NMR. It's slightly more complex. However, we can imagine performing those experiments, for example, waiting enough time to fully equilibrate our system. But then, okay, those experiments could be very time-consuming because, Zbigniew, yeah, you're absolutely right. Usually for carbon-13, T1 relaxation is relatively long, so we would have to wait significant, let's say, time in order to get our to have representative integration underneath our peaks.
Maybe I add something interesting. These sidebands are traveling on the curve of the top of the chemical shift anisotropy shape. If you change the frequency of the rotation, they change their positions, as Jacek mentioned, yeah? But the amplitude of them change like a shape of the isotropic density. So you can get you can get the fall. Okay, now it's all right. You can get the fall. Get the fall, the shape of the CSA chemical shift anisotropy shape, changing the frequency. I often to meet with you, for example, in Uber, to discuss about in the Mars.
Let's do it one.
Thank you.
Thank you.